This is, again, from Chapter 5 of the book, like most of the other material this week. So Monday we learned about vectors and linked lists, and I talked about this idea of abstract data types. On Wednesday we learned about stacks and queues. And today we're going to learn about 3 more collections called sets and maps and lexicons. So here we go. A set is a collection that doesn't have any duplicates. Sets are usually fast to add, remove, and search. Those are the core operations. A lexicon is kind of like a set, but it's a particular usage. It's storing words of a dictionary or language. A map is more complicated. We'll talk about it a little bit later today. Maps store pairs of things that are connected to each other. So I'll come back to that. I want to start with sets first. So what's a set? Well, here's an example of a problem where I think a set would be useful. Let's say we want to write a program that counts the number of unique words in a file, a text file on the hard drive. But maybe it's a big file like the Bible or Moby Dick or the Constitution, some large file, decently large file. I want to count the unique words. So like if the word the occurs 5 times, that counts as what? So anyway, what can we use to solve this? Well, I'm going to talk about sets, but let's pretend we never heard of that, or let's pretend there's no such thing as that. So let's say we really like vectors. We've used vector a lot in our lives, or maybe something equivalent to that, like an array list. So what if I had a program called sets? And suppose I'm going to write this word counting function. You pass it in a file name, and it'll read the words in that file. So you pass in a file name. Now, one thing I'm doing here that I've already written, there's a library that comes with our Stanford systems called timer, where you can say start and stop, and it'll tell you how much time took place in milliseconds. So I'm going to use that to do like a runtime test to see how long something takes to run. OK, I'm opening up a file, the file name that they specified, and then I'm going to read the words from the file. One thing you might notice is I'm using this arrow syntax to read words. You know, you could do cin with an arrow to a variable. You can read from the keyboard. You can also use that from a file stream. That reads a word at a time. Those other commands that we learned, like getLine, those are fine too. But those read a whole line, and then you have to slice apart the line to get the individual words. If you make a string and then use this arrow, it actually just grabs one word, which is really nice. So this is a loop that grabs all the words from the file one at a time. Let's suppose we've never heard of a set before. So we've decided the way we're going to count the unique words in the file is using a vector of strings called words. OK? So as we see each word, we're going to do words.add word. We're just going to put it in a vector. But we don't want to include the duplicates, right? Don't put the same word in the vector twice. So how do I avoid a duplicate? Well, you could imagine I would say something like, well, if the vector already has this word, then don't add it, right? Like, so is there a contains function or search function or something on a vector? Let's look. Words dot. There's no contains. Maybe there's an index of. No. There's a bunch of operatos. I don't see it. So, OK, there's no built-in method here for like searching for stuff in a vector. That's kind of weird, right? OK, well, obviously, whoever designed the library, this must be an oversight. Clearly, they meant to put this in, but they got lazy or something. So what I've done is I've written us a function called contains. It takes a vector reference and a string, and it loops over the vector. This is pretty simple code. It loops over the vector. And if the element I is that string, it will return true, right? Because then it's contained there. And if I don't see it, I'll return false. That seem reasonable? Like that'll tell me if a string is found in the vector. You might think, isn't there a faster way to do that or something? But I mean, what else can I do? I mean, I got to look at all the words to see if I have this word or not, right? So OK. So now I can ask whether a vector contains something. So let's go back up here and let's say, well, I don't want duplicates in my vector. So if it's not true that the what is it called, contains words, comma, word. If that vector does not contain that word, then add it, right? OK. Now that we've done that, at the end of this while loop, the vector should have all the unique words. So to count the number of words, how do I know how many words there are? The size, the length of the vector is the number of words, right? OK, so down here, it'll say the file contains how many unique words? Well, I'll just break my string and say words.size. And then I'll say that many unique words, right? And then also, one thing that I wrote ahead of time was the timer will stop, and it'll print how long it took to do that. OK? So, and I think up in the main, all of this code is being run on Moby Dick, which is, how large of a document is that? That is a large document with, what, 20,000 lines of text. So let's see what happens. Here goes. Compile. Any of you guys watching Game of Thrones? I like that lady with the dragons. She's cool. Oh, man. Input stream. What? Oh, is this... what's going on in here? Include f stream. Sorry, this is something I'm going to do later. This is another file in the same project. Let me try that. Ah! What? I think I forgot to include something. Is that in... Oh, it's in another file. Sorry. When you use files, you have to include this library called fstream, file stream. And usually when I give you these files, they'll already have all the included statements on the top. Come on. This isn't even the thing that I'm trying to do right now. This is some other file. Sorry. Don't look. OK. Sorry, guys. Let's run it. OK, so I hit run, and nothing's happening. But that's because it's doing the counting, and it doesn't print anything until it's done. So the console hasn't even popped up yet. But you just have to take my word for it. It's going to be awesome when it finally appears. It'll blow your mind. It's the best program ever. And it takes a while to run. Oh, come on. Wow, that's not a very good picture. Look at sad Hitler. He's so sad. He's so sad at this program. Now, you probably think like we have a bug or something, right? But I don't think we have a bug. I think it really is running. I mean, I'm kind of just making a point here that this program could be correct, but it's really slow. And I think that's an interesting thing. You know, we sometimes talk about efficiency. Sometimes you guys ask me about efficiency. You know, does it matter if I declare 2 variables instead of 3? Am I going to waste memory? Am I going to waste time? Something like that. And, you know, some of those little things don't matter. But when you're, oh, hey, here we go. I knew it would come back eventually. It took 77,000 milliseconds. That's about a minute and 17 seconds, right? So here's a case where you can have a correct program and it's very slow. You might say, well, maybe that's just how long it takes. Maybe that's how long it takes to read such a large document and count up all the words, right? Because that sounds like a really complicated thing to do, right? So maybe that's, you know, something being slow doesn't mean it's bad. You can't solve every problem in the snap of a finger. But my claim is that we're just using the wrong data structure to solve this problem. And when you look at this code, the code looks pretty innocent. But if you think about it for a second, this code takes quite a long time. Because every time I read a word, I have to ask whether the vector contains that word, which means I have to walk all the way across the vector to look for it. And the bigger the vector gets, the longer it's going to take me to walk around on the vector looking for things. And so every word I read, I have to do another walk all the way across the vector, right? It's just a pain. I mean, imagine it's like anything where you have to look at all the data points to find the answer can take a long time, right? Like if I'm looking for a particular person in this room, and I got to ask every single person, is that you? Is that you? Is that you? That's going to take me a long time. And then every new student who walks in, if I have to ask everyone again the same question, it's just taking a long time. It'd be easier if I could just call out, are you here, Joe? And then Joe would stand up if he was here, right? So anyway, this collection is wrong. Even Hitler doesn't like it. Let's maybe do something better. So a set is a collection library that you can use. And it enforces a constraint that no duplicates will ever be inside of it. So if you try to add the same thing twice, the second one will silently be discarded. It will not be added a second time. Now, most sets don't support very many operations. We learned when we talked about stacks and queues that some collections don't have as many operations as like a vector. But that doesn't necessarily mean that they're bad. Because what that might mean is they do fewer things, but they do them really well. They do them really efficiently. They do them using not very much runtime or not very much memory or both. That's kind of the idea here. if you optimize your collection only for adding things, removing things, and searching it for something, you can make the collection very fast. And I will teach you what it's doing internally later on, but not today. One thing we give up, one thing we sacrifice when switching from, say, a vector into a set is that a set does not use the brackets and the int indexes the way a vector does. Just like how a stack or a queue, you don't use bracket int I to jump to a certain index. And so we have to sort of let go of that way of accessing data. We have to look at the data inside in a different way. OK. If you want to use sets in C++ using our libraries, there are two collections that represent sets. One of them is called a set, and the other one's called a hash set. And what's the difference? Well, the hash set is slightly faster, but the order that it stores the elements is all jumbled up and unpredictable. That might matter to you, or it might not. The regular set is slightly slower. It stores the elements in a sorted order, so like A to Z, or lowest number to highest number, that sort of thing. So they're both pretty useful. The way that you decide which one you want to use is, do you care what order the elements are stored in? If you do, you might want set. If you don't, you probably want hash set because it's faster. It's not a lot faster. We'll measure it in a second. How do you use this thing? Well, you include the appropriate heading, either set.h or hash set.h or both. Then these are the different operations you can do. Basically, add, remove, contains. Those are the main ones that you get. There's a few others like size, is empty. There's a few other things. And I mentioned sets don't store duplicates. So if you say add and you add the same thing twice, it doesn't add it the second time. And the implication here is that all these methods run fast. And notice how there is a contains method. The vector doesn't have a contains method. We wrote one in our program just to try that out. But it turns out the author of the vector intentionally did not include a contains method. Because it's so slow to search a vector for something, the author of that library, who's a Stanford professor, Eric Roberts, he didn't want you calling contains on a vector. He wanted you to pick a better choice of a collection for that operation. So he didn't want to provide this operation that is implemented badly. OK. There's a few other things you could do with a set. It actually has operators. You can ask whether one set is equal to another. You can also add sets to each other, which performs a union operation. You can use a multiplication character to do the intersection, which is the elements that are in both only. You can also remove all elements of one set from another set. So those operators are kind of useful. Now, just to give you an idea how this thing would work, you see my little Socrative logo. I'll ask you a question on Socrative in a second. But before I do that, let's go back to this code just for a second. Remember, this one took like 77 seconds to run? OK. What if I just change this into a set? And you might say, well, which one do I want? Do I want the regular one or the hash one? It depends whether you care what order the words get put in there. So is our program doing anything that has to do with order? Do we care the order? Seems like we don't. All we really want the set for is to ask, have I seen this word ever before, right? If that's all you want, you don't care about the ordering. So maybe hash set's OK. Now, if I try to compile that, it won't like this line, because there's no contains function in this program that takes a set and a string as parameters. So it's OK. It's just we wrote it the wrong way. It should be if it's not true that the words dot contains word. You understand? Like that method is inside of the object now. So I compile that. Now it compiles. I run it. Remember, what was it, 77 seconds? Done. That's fast. That's really fast. And it's still correct. It produced the same answer. I probably should have written down what the answer was to make sure it didn't produce a different result. But it did do it. Like, you might not even trust that it really did it, but it's done. And the main difference is that this is so fast. So somehow, the set is storing this data internally in a way that makes it really fast for it to go look up things. And you could imagine all kinds of ways that it might be accomplishing that. And I'll teach you later. I mean, if you're really curious, the slide alludes to this a little bit. The hash set stores using this thing called a hash table. You could Google that if you were curious. And the regular set uses something called a binary tree. You could Google that, too. I'll teach you how to do both of those things internally during this course, but not fully today. Yeah?
Does the line highlight is necessary? Because I think the set will already contain a unit. And you don't need to determine the origin.
That's a great question. She says, do I even need this highlighted line? Even if it's already contained in there, why don't I just go ahead and add it anyway? Because it'll just reject it the second time, right? So I think you're right that I could just delete that line and the code will still function properly. You might wonder, maybe it's even faster this way because I'm not calling contains. I don't know. I don't remember how, was it 110 millisecond or something? It's, yes, I saved a millisecond. Yeah, we did it. But I think that's honestly, if I ran it 5 times, it'd probably go up and down a little bit. So I doubt we really saved anything measurable there. But it still is correct and it still works. There were some other hands up. Yeah.
So I have a two-part question. I was wondering if sets store like in the least to the greatest order. So like for integers, like the least, and like for strings, like they start with A. And then my second question was, I don't really see why this code would be one word at a time. So could you go over that if
Oh, OK. So she had 2 questions. One is like, if I use the regular set, not the hash set, does it store the words in ABC, like A to Z order? Yeah, it's like alphabetical order if they're strings. If they're integers, it's like ordering of the ints. Smaller, lesser numbers or negative numbers are over there on the early in the collection, and large positive numbers are over on the right. So it's ascending order. Now, one thing I didn't do, and you had a second part I didn't forget, but one thing I didn't do, it was using hash set. It took about 100 milliseconds. How long would it take if I used the regular set, the one that sorts? Maybe I said that was slightly slower. I'll recompile it and I'll run it again. It took 204 milliseconds. So it took twice as long. You might say, oh, I don't want that. That's slower. But look, I mean, sometimes you care about the ordering. And so if you're willing to sacrifice a little bit of speed, then maybe that's worth it. A lot of students always use set because they don't even think about it. They say, oh, I need a set. So they're at set. And I always tell them, oh, come on, you could go faster, man. Try the hash. It's good stuff, man. Never mind. But some people don't roll like that. So anyway, it's a little bit slower. Now, her question also was, like, what was this business of the words at a time? The point of the program is I'm counting the number of unique words in the file. So, like, if I go back to the where is it? Moby Dick is the book that I'm using here. So, like, I just want to count up, like, call is a word, me is a word, Ishmael is a word, some is a word, yours is a word. But if I see the same word more than once, like, I don't know, are there any repeated words here? There's of here and there's of there. I don't want to count that as 2. I want to count that as 1. So by putting the word of in the set, eventually when I get to that of, it isn't going to count it a second time. So that's why. So what I'm doing with this code here is when you use input arrow word, the meaning of that arrow is, you've used getLine to read a line from a file, but that arrow reads a word. It chops the words apart. So that's a nice loop to read a file, a word at a time. So that's all I'm doing there. Anyway, so was there another question? Yeah.
So if somewhere in there there's like a letter or something that's not a string, would the while loop like skip over that or like make that into a string?
Yeah, so what does it do for things like punctuation or like it skips over spacing? It grabs anything that's not space and calls that a word. So our program is a little bit fudging it because Ishmael period is a word and Ishmael without a period would be counted as a separate word. So really I should probably like strip, I kind of just fudged it because I didn't want to worry about that too much. And so the count is actually slightly wrong because of that. And there might even be some capitalization issues there where that would count as 2. But the problem is if I process every single word with a bunch of manipulations before I add it, then that actually non-trivially increases the runtime as well. And so I wanted to show off how fast this thing is. If the delimiter, if the limiter of the power and the speed of this thing is the collection, this thing gives you almost no overhead. It's really fast. That's kind of what I wanted to focus on. Was there any? There were some other hands up. Did I get everybody? I'm always happy to have your questions. OK, so I did say I wanted to do a Socratic question with you guys, right? So let's play Socratic real quick. If you didn't log in, you can log in at the end. I'll put it up again. I still want your vote. Quick question, multiple choice. Here we go. So what's the question? Well, here's a piece of code where I declare a set. I add and remove some stuff. What do you think is in the set at the end? A, B, C, or D? Take a look. Talk to your partner if you like. voted yet? Let me look how many votes. 126. Okay. About 10 more seconds, and then we'll show the votes. You haven't voted yet? Just give your best guess. All right, let's see what you guys said. A's and B's. Okay, A got the most, but it's pretty close. Let's look. A's and B's. Well, guys, come on. You should be able to eliminate one of these choices quickly. We're using a set, right? Not a hash set, we're using a set. What does a set do with the order of the elements? They're sorted, right? So it can't be B. Those are not sorted order. It also cannot be D, right? Those are not sorted order. So you know it's either A or C. And I mean, if you walk through these, we had some 74s, but we removed that. I mean, I think A is the right one, right? And I mean, B has the right elements. So if you put B, it's not a horrible answer, but they would be in the sorted order. Isn't B the order they would be in if this was like a vector and you just put them at the front and then, right? Isn't that kind of what it would be? I think that's why I made that answer be that way. So you know, you just have to watch out for the ordering when you're thinking about a set. Yeah. Yeah, that's a good question. I removed something that isn't there. When it's not present and you try to remove it, it just does nothing. So it's fine. And of course, later we add it, so it is in the results, even though we removed it previously. Oh, my fiance got the answer wrong. She said it was C. She doesn't even know. I just asked her to guess, and she said C. Sorry, honey, 1 for 2. You're wrong. Okay. You can, if you want to like look at all the elements in the set, loop over them or something. Again, we can't use bracket I. That doesn't work. So instead, you use that for each loop. You say for, and then you say, so that one right here at the bottom doesn't work. You say for, you know, string s in words, run these statements. So this is a syntax that's kind of like a for loop, but instead of using int indexes, you use a shorter syntax where it loops over the contents and gives each element a variable name. And it's a little bit weird syntax. Sometimes people have trouble getting used to this syntax, but it's not that hard to use. All you do is you just come back here and you say, like what, down at the bottom here? If we wanted to actually loop over all the words, I could just say for each string s that's found in the words collection, I want to print s endl. That's it. It's like if I said for each int I, print element bracket I. That's kind of similar, but we don't have those indexes, so we just use this kind of syntax. What order do they come out? Like if I print them, what order will they print? Well, if it's a set, it'll print them in the sorted order. And if it's a hash set, they print in kind of a weird jumbly order. Maybe what I'll do here is just as an illustration, I'll say like if words.size is at least 10 break. I don't use break very often, but I'll just like stop the loop after the first 10 words just to show you. If I run this thing and I print the words, these are the words. Now, those don't seem to be in any particular order. That's because I used a hash set. If I change it to a set and I run it again, then these are the words. Wait. Wait, let me see that again. OK, so the capital ones are first, C, D, H, M, M, O, T, W. And then there's a lowercase word at the bottom. So if you were bothered by all the capitalization stuff, you could do something like word equals to lowercase of word. You know, that would be one way that you could address that issue. And now those are the words that come out. So they're sorted now because I used a set instead of a hash set. When I ran it before on the hash set, they were just kind of all random jumbly order. Okay. So, okay, imagine the following variation of our word counting problem. Now, instead of, wait, no, sorry. That slide was saying, let's go back and write the thing that we already wrote. Sorry, I was being a little confused. Hang on. This is what I meant to be on. let's write a variation of the last program. But instead of just counting the number of words, we also want to know how many times each word occurs. So the word the occurs 100 times. In our current code, we just collapse all of them and just count that as one word. This time, I want to know that there were 100 copies of that word. But you might think, OK, let's go back to the vector or whatever now. But that's still slow, because I still have to like loop over it to count all the occurrences and stuff. So I don't think that's an ideal collection either. What would be better? Well, let's talk about something called a map. Maps are a little bit harder to understand, I think, than any of the other collections I've shown you this week. Because all the other ones are what we call linear structures. They store a single collection of elements in some order, and you can loop over them. It's a fairly simple concept. But a map doesn't do that. A map stores pairs of things. You don't add just a single element of data to a map. You add two things to a map. And then what the map will do is it will connect them to each other. It will associate them with each other. And then later, you can use the one to find the other one. So a classic example, like real-world example of a map would be a telephone book. A telephone book, you might think it's full of pieces of data, like phone numbers. But it's not really just full of phone numbers, right? It's full of pairs, name and phone number. So if you're adding data to a phone book, you add a name and a phone number. And then later, when you want to use a phone book, usually the reason you're using it is because you have partial information, but not the rest. You know the person's name. You know the business's name. You just don't know their phone number. So you turn to the page of, and then I remember just now that you people probably never use a phone book in your life, right? This old people thing used to be called a phone book. Actually, wait, let me back up. People used to read these things called books. There was a particular kind of these book things that was called a phone book. And yeah, you had numbers in it. Anyway, you have the person's name. You just don't have their phone number. So you look up the name, and then the number's there next to it. So that's kind of what a map is. A dictionary is another good example. Words and definitions. You add a pair of those things to the dictionary. Like, every year there's some goofy new word that gets added, like twerking gets added to the dictionary, But they don't just add twerking. It's the word twerking and then a definition, which means like dancing like a crazy person and jiggling your butt around, right? Something. So that's now in the dictionary. So then later, somebody doesn't know what that means, but they have the word. They have half of the information. They just need the other half. Anyway, that's what a map is for. And the three operations that a map usually does is essentially the same as what a set has. You can add, remove, and look up. Add, remove, and search. But they're called different things here. They're called put. Putting means adding a pair into the map. Getting means retrieving the other half of a pair. You have one half. You want the other half. So it's like a lookup. And then the third operation is just removing a pair. Okay? Now, one thing I haven't really mentioned, but it is important, is that the associations are usually one-directional. And you could understand this if you had a dictionary or a phone book. If you have the person's name, it's easy to look up their phone number. If all you have is a phone number, but you want to know whose phone number that is, the phone book is not laid out to help you do that quickly, right? It's sorted by people's names. It's not sorted by phone number, so you can't look up reverse very quickly. Same thing with a dictionary. You're like, what's that one word that means jiggling your butt around? It's like something. You're not going to read through the whole dictionary to find the page that has twerking, because you don't know what the word is. So the same thing with a map. It's good for finding the associated piece one direction, but not the other direction. So here's what you can do with a map. Map has this method called put, where you put a pair of things in, and you're associating the two chunks. We call the chunks the key and the value. And there's two syntaxes. You can say put, or you can use brackets. You can say m bracket Susie equals this. So I'm storing that Susie's phone number is that. Then later, if I ask the map, hey, what's associated with Susie? What's the other half of that pair? It'll say, it's this phone number. You can look that up. Just like with sets, where there's a hash set and a set, there's a hash map and a map. And the properties that they have are similar. The hash map is jumbled up order, but it's faster. And the regular map is sorted by the order of the keys, like the people's names in the phone book or the words in the dictionary. But it's slightly slower, slightly. When you declare a map, you have to use those brackets for the type of data, but you actually have to put two things in the brackets, because you might be associating pairs of one type with another type. Like a phone number might be a string of a person's name mapping to an integer of a number. So it might be string, comma, int. Or it could be a string to a string, first name to last name. So you have to write the types of each half of the pair in those brackets there when you declare a map. Here are the different methods you can call on a map. You can construct it. You can put things in it. That's like adding. You can get things back out by searching for them. You can remove things. You can ask for the size, and so on. OK? So one thing you can do with maps, one particular way that maps are useful is you can use them for tallying and counting. So you might have seen this trick before. If you want to count occurrences of digits in a big integer, how do you count them? Well, you can make an array of size 10, and then in index 0, you count all the 0 digits, and in index 1, you count all the 1 digits, and so on. And so in that number right there, there's 3 copies of the number 2. So index 2, I'll store a 3. And you could do that sort of thing with an array. But how do you count like the votes for candidates in an election or something? If all the R's are Romneys and all the O's are Obamas or whatever, how do I count those? Well, you could pretend that R was index 0 and O was index 1. Or you could come up with some mapping like that, right? But a map, that's kind of what a map does. One way of thinking of a map is it's kind of like an array, but the indexes don't have to be ints. That's the way I think of it. With an array or a vector, you say bracket 0, bracket 1, bracket I. With a dictionary, you could say the definition of bracket twerking is shaking your ass around like a fool. And so now twerking is like an index in that data structure that you can store stuff at. So that's pretty powerful. It's like an array. It's a generalization of an array. The indexes don't have to be ints. They don't have to start at 0. OK, how does this relate to our problem that we had? Well, this piece of code that we were writing, that we are going to write, it's about tallying words in a file. So I have to rename this domain something, so it won't run that. And then I want to go to this maps.cpp. So this one is word tally instead of just word count. And let's use the same book, Moby Dick. Now down here, I'm still opening this file. I'm still reading in the words. And now I just have to decide what to do with them. Now, how do I count these words? Well, I want to, oops, what happened? Whoa, there. I want to count the words. So for each word, like the word the, I want to know that that word occurs 29 times or something like that. But I want that for every word in the book. How does a map help me do that? What do you think, sir? What does a map do?
You can make a map such that you're mapping the string, which is the key value, I guess, is the key is the string, and you have an integer for the value, which is initialized to 0. And every time you encounter a certain key, you increment the integer in that.
OK, what he said was make pairs that are like this, where the word is the first half of the pair, the key, and the number of times I've seen the word is the value. And you said let's initialize that to be 0. We had never seen it before. But then every time we read in that word from the file, we'll increase it by 1, 0, 1, 2, 3, 4. And so we'll store a bunch of tallies mapped to each word in this map. So that sounds like a great idea. So we'll make a map from strings to integers, and we'll call it tally or something. And now down here, when I see this word, the idea is like, if this is the first time I've ever seen that word, then I probably want to store a pair of that word I've seen one time, right? So like, if I've never seen that word, if the tally map does not contain this word in it yet, then I will put in a pairing from that word to the number 1. Do you understand that? If I've never seen the word before yet at this point, but if I have seen the word before, that means I have some sort of mapping already, like the maps to 17 or something. So what should I do? I've seen 17 copies of the word the, and I'm continuing to read the file, and I see another the. What should I do now? Yes?
Can you do a tally word plus plus?
I need to plus this to get this to be an 18 instead of a 17. I'm counting. I've seen it one more time. So the long way of doing this, I heard what you said, but I'm going to slightly modify what you said. So the current count of these things is associated with this word. I'll say int count equals tally.get what's connected to this word. Get the count that's connected to this word. And then do count plus plus. But to make sure that goes back into the map, I have to put it back in. Tally.put count word, comma, count. So change the mapping to be the same word with a higher count now. OK? Let's try it. So down here, I'm asking the user to type a word that they want me to search for. And then I will show them how many times that word occurs. So if they typed a word, how do I know how many times it occurs? Well, that's tally.get what's associated with that word. And so I'll print that out. Count times. OK? So let's try that out. Whoa, that got really big. Bless you. Let's run this. So what's the word to search for? And so are we doing Moby Dick? So if I do whale, whale occurs 495 times. How about the? Oh, that's a lot. Ishmael. White whale. It's a white whale. I never read Moby Dick. I don't know. Kill. Die. Hello. 0. I've done this example before. And so one time I ran it on the Bible. I have the entire text of the Bible. And I compiled it and I ran it. And I typed in like God and it said like 3 times.
Yeah, Ishmael occurred more than twice in Moby Dick.
Yeah.
I think maybe the punctuation is.
Yeah, so I typed in like Jesus, I typed in devil, I typed in all these things, but this last time I did it, it did like 0 copies of the word Jesus or something. And I'm like, what? Turns out it was case sensitivity problems, and I was like, man, do I have some weird like hippie version of the Bible today or something? But I figured it out after class. Okay, no, so this is working, and I hope you saw, like I didn't do a timing test with that timer thing, but it was fast, like it popped up right away. It counted all that up really fast. I want to come back to this code. All of this code is basically our way of saying, if I've never seen that word, then put it in the map with a count of 1. If I have seen it, then pull it out, increase it, put it back in. There is a shorter way to write all of this code. So let me tell you something. If you want to access a map, you can use brackets. So instead of like, wait, let me copy this and paste it down here. It's the same code. So tally.put word, comma, 1. An equivalent way of saying that is tally bracket word equals 1. The brackets are a way of jumping to that pairing for that word. That's a short syntax for the same operation. You can use that to access or modify. So you can say tally bracket word here, and then you can say tally bracket word. Oh, what did that do? Tally bracket word equals count here. So you can do that, right? OK. The other thing is you mentioned plus plus. So all of this is basically I want to increase tally bracket word by 1. So you actually can say, instead of all that, you can say tally bracket word plus plus. If I've never seen it before, then store it as 1. If I have seen it before, plus plus it. Do you understand? Those are the same. But wait, let me blow your mind just for a second. What if I didn't do this test here? I didn't check whether it was contained or not. If I just always did the plus plus version, what would that do? Well, if I had never seen the word before, it turns out if you try to go get what's associated with a key, with a word that you've never accessed, it just sets it to a default value. Whatever's the default value for that data type of the value type of int in this case, the default value is 0. So if you do tally word plus plus, and there was no tally word, it creates tally word, sets it to 0, and then plus pluses it to 1. So it turns out that all that stuff in comments could be replaced by tally word plus plus, and it still just works. It's pretty cool, actually. Just if you don't believe me, I'll run it again. But how many times do we have God? Jesus. Jeebus? No, none. Okay. Well, anyway, it's still working. So that's an example of a map. It's a powerful structure. The thing that's important to understand is you are always storing pairs in a map, never individual pieces of data. And it's able to look up the second piece quickly if you have the first piece. That's the key here. Okay. Questions so far about maps? I want to show you one more thing. Clock's ticking, so I don't have a ton of time. I'm going to skip a Socrative question real quick. It gets real exciting when you do collections of collections. They're called compound collections. You can have a vector of sets. You can have a set of maps. You can have a stack of queues. You can have collections inside of collections. So you just declare them like this, a vector of sets. One thing is you're supposed to put spaces between the angle brackets, or else on some computers it doesn't compile properly. But otherwise, that's how it works. So here's a quick example. Imagine I wanted to keep a collection of all of of a bunch of people's buddy lists, a Facebook buddy list or something. What you would do is you'd have a map from strings to set of strings. And what that means is if I give you the key of Marty, then the associated value will be the set of all Marty's friends. So like if I give you, Kevin, then the value for that will be a different set, which is the set of all Kevin's friends. So it's a mapping from people's names to the set of names of all their friends. And so this piece of code creates that structure, and it stores data such that Hal's friends with Mar, Jim's friends with those three people, and Mar is friend with Helen and Stuart. It's pretty powerful, that idea. Now, an example of where you could use it would be to find anagrams of a word. If I gave you a big dictionary file, and I said type a word, and I said show me all the anagrams of that word, how would you do it? Well, of course, I want to use a compound collection for this problem. So what you can do is, imagine if I gave you a function where you give me a word, and I'll sort the letters of the word and give you back the word like sorted. So if you give me swell, I'll give you back ilzu, because the E's come before the L's in alphabetical order and that sort of thing. I'll sort the letters and give it back to you. How does that help you tell something about anagrams? You understand anagrams, rearrangements of the letters, the same word? How does sorting the letters help you? Any ideas? Yeah?
That gives you your key.
It gives me a key. OK, tell me more. What do you mean?
When you any anagrams are going to have the same value when sorted.
All words that are anagrams of each other will have the same sorted form. That's true.
Yeah. So if you were to set up a set that had the AEFR, a map of AEFR, and you could store both fair and fear in the secondary set inside of that.
OK, I really like your idea. So he says, let's make mappings from sorted forms of words into all the words that have that sorted form. That's how we'll find collections of anagrams. So I'm running a little short on time, but I think I can do this. Got fast fingers here. So here's anagrams.cpp. I've got a sort letters function that I've already written. So I'm going to read words from a file. I get the words, and then I want to put them into a map. You said let's make a map from strings that are sorted forms into sets of other strings that have that sorted form. So let's call this anagrams. Now down here, what do I do as I read each word? Well, you said I wanted to grab all the sorted forms of the word. So I could do string sorted equals sort letters of the word. I could do that. And then what? Well, if I went to the anagram collection and I use sorted as a key, then there's a set there of all words that have that sorted form. And what do I want to do with that set? Yes? I want to add in the word I just saw. So if I just read the word fair, I want to remember that fair is a word of the set of words whose sorted form is afer, if that makes any sense to you. So store it in my anagram collection. That's a key line right there that I've highlighted, OK? And now down here, the user will type in words to me, and I want to show what all the anagrams are of that word. How do I show what all the anagrams are? Like they type in later sacred, and I want to print out all the words that are anagram of sacred. Where are those going to be found? They're going to be found in the anagrams collection. Where? Bracket word. I need it to be the sorted form. Sorted equals sort letters, word. The anagrams of sorted. That's the collection, the set of all the words. If I want to print them out, one per line, how do I print all the elements of a set? I could do cout like that, but I want to print them each on its own line. Do you know how I do that? This thing is a set. How do you loop over a set? You do for each string s in that, cout s, endl. The just try it real fast. If you type, oh, it's gathering the data. Now it's done. Type a word. Scared. There's all the anagrams. Shell. Seal. Ball. Oh, there's only one. Ball itself. You see that? I mean, just using this one collection and a couple lines of code, I'm storing all the anagrams.